Okay, well, looks like we're missing a few people, but we do have to start quickly because we have a lot to do. Okay, well, we have to start anyway. So we have finished chapter 11, and now in chapter 12, we don't have time to go through it, but we only need to make clear a certain part of it in order to go where we need to go. So, and the same thing with chapter 13. So let's just do that now. Pardon me. And so we just need to understand the basics of OOP, object-oriented programming, and then how to do that in R. So is there anybody who's not familiar with OOP, object-oriented programming style of programming? If you took my Python course in the last 2 years, you probably had some introduction to it, or you might have had it otherwise. Anybody not seen OOP before? Classes, the idea is classes and objects.
Professor, I think I have been, it has been explained before, but I never really get it.
Okay. Well, it's in the way we need it, it's pretty simple. So the way it's usually introduced in a textbook or in a course is usually they say, suppose you work in the academic office and you have to, they want you to do some programming, and they want you to represent, do something about students, some programming about the students. So of course there are many, many students, and you don't want to write one program for each student. That would be insane. So the idea is that you kind of make up a kind of a blueprint of what students, what are the things you need to do with students. So you say, okay, well, I'm going to need here on the screen here, I'm going to need to know their major. I'm going to need to know their zip code and their GPA, maybe. Let's just make it very simple for this example. But there are probably other things you'd want to know also. But you don't need to know everything about a student, of course. So you just identify the things that you need to know about a student, and maybe you also need to know their name. And then, like, for now, there's also like a function that you need. So these are not functions, these are variables. But also there's maybe some functions that you need, like maybe you need a function that will check somehow based on this, which I guess you wouldn't be able to check it based on this. Actually, you need some other variables as well, but to check whether they're qualify for a scholarship and like how much they, something like that. So maybe there's other data in here as well that you need in order. Of course, the GPA would be an important factor, but there might be other factors. But anyway, let's just make it simple. So, so you decide, okay, there are certain variables that I need and certain functions that I want also. And then you just sort of put that together as a blueprint of what we mean by a student. And in OOP, that's called a class. The blueprint is called a class. So you make what they call a class, a student class, and it has will have each. It has a major and a zip code and a GPA, and it defines this function as well. And then the way OOP works is once you write this class, then you make instances of the class. So there might be an instance of the class for Dao, and there might be an instance of the class for Diep, and there might be an instance of the class for Utsav, and also for, what happened to our other student? Oh, okay, you're there. and Hong and Hong and Sela and Tomohiko. So we'd have how many instances? 1, 2, 3, 4, 5, 6 instances of this blueprint or of this class. So each one of them would have a major variable that you could set, a zip code variable that you could set, a GPA variable that you could set, and you can also run the Scholar OK function on each one of them. And that's the idea of OOP. That's the basic idea. Then, there are other features of it, but that's the basic idea. So once you've written this so-called class, and maybe maybe it was called student, then you could create a student like this. You could create a student, like we'll create a student with a name of John Smith and a GPA of 3.8 and a zip code of this, and this is their major, and that's how you create the student. Once you've written this class or blueprint, then this could be like our way to create such a student with this information. Now, by the way, this and this don't have to be the same. Now, it sort of makes sense to give this the name John Smith, just so you know sort of which student this is. But this is just the variable name. You could have called it X or Y or Z or P or whatever. It's just the variable name. The name of the student is here. But I guess in this case, you might use the person's name because it just makes it easier when you're working with it. So that's but this might be how you create such a student. And then you could check. This would be like the syntax for checking whether they qualify for a scholarship. In other words, you put this is called the instance, the name of the instance. This is called the instance name. This is the name of the person, but this is the instance name, the variable name. So you put the instance name and then dot the function. And that's how you would run a function in OOP style syntax. So that's the idea. And then you could also create another student like physics, zip code, GPA, name, instance name, and you could do the same thing. Naomi Osaka, is she eligible for a scholarship? So this is the style. You could create many, many, many instances this way, many, many, many students. You'd be able to do the same kind of thing with all of them. So this is a strategy for writing your programs, really. Like you could obviously write programs another way, but this is a very, very nice structure to do. So that's the idea. And as I said, there are other properties. So, and one more thing about the terminology is that we don't call, if we decide that we're going to use these major, zip code, GPA, we're going to include those as the variables. We don't call them variables. We call them, they're different things, but we call them either fields or properties of the class. Just so that you know, if somebody says there's a field called GPA, that should tell you, oh, that's probably from a class, not just a free-floating variable. Okay, so it's just helpful to know that it's probably inside a class that it was defined. And so they're called fields or properties. And the same thing, we distinguish, we don't call this a function, although it is a function, but we don't call it a function when it's defined inside the class. We call it a method. So if you hear that it's a method, then you know that it's a function that was defined inside some class. That's the idea. Now maybe this is not exactly the right syntax to do in R. Maybe this is the syntax in Java, or maybe it's the syntax in Python, but it's it's not exactly how it's done in Java, but the idea is that the same. So, so we're going to rewrite our neural network class using this kind of style. Now, we're going to create some methods like the backprop method and the forward method and the jcost method. And maybe we'll have maybe we'll call our class neural network, and maybe the things that we need to specify in here are the inputs into the neural network and the outputs, and maybe the number of layers in the hidden layer. So maybe that's what how we design this class. So we have to put that stuff in there. And so that's what we do. So we're going to create an instance of our neural network, and we're going to call it NN1 example 1. Okay, so that would be, now, actually the R syntax is not exactly like this, and it's typically like this. There's another version of another way to do it, another style also. But this is, you'd say, once you created that, once you write the neural network class, which I haven't shown you how to write it at all yet. I'm just saying once you write, I said, if you have the class, you can create an instance like this, or you can create an instance like this, but we haven't said how you write the class yet. But anyway, once you write the class, this is actually how you do it in R. So you give the name of the class, then $, and new. Now, most languages, well, yeah, so like that, okay? And then if you want to run, once you create this instance, you don't do it like this. This is more like a Python style or a Java style where they use the dot notation. In R, it's like this. Okay, so that's how you would that's how you would run the backprop function or the backprop method. Okay, so that's the basic idea. Now, it's a little bit, the way we do it in this chapter is just kind of practice for how to write, how to do OOP in R, because we don't, it's kind of, you would say, well, why do you need to create many, it's obvious why you need to create many instances of a student class. You want an instance for each student. Well, why do we need many instances of a neural network? We don't. We just need a neural network. We don't have to have many of them. We just have one. We don't have any reason to run 10 neural networks. We just run one neural network. So it doesn't exactly make sense to do it in this case the way we're doing it, but it will make sense when we restructure it and we do it in a different way, but using classes in chapter 14. It'll make a lot of sense. So here we're just getting practice with how to write a class in R, and we're still going to use the neural network example. Maybe it wasn't such a good choice to use the neural network example to show it, because the neural network example is pretty complicated, and we're just introducing OOP. Why should we choose a complicated example? Maybe we should just do student and a simple one. But anyway, probably we should have. But anyway, so we're going to do it in R, and there are different iterations or different ways to do it in R. Like they started out doing it one way, and then they changed it a little bit, and there's another way, and then they changed it a little bit, and there's another way. Because honestly, in R, it's not so typical to write classes. But certainly, if you're writing a neural network, you would want to do it with classes. But typically in R, you're not doing that kind of thing, and it's not so often that you would want to write a class. But anyway, we're going to learn how to do it. And this is the most recent way of being able to write a class. So you use this function called setReferenceClass, and it comes from a S5 system of R. R has developed over time, and the S5 is a certain subset of R. Okay, so the way that you do it is like this. So you say setRefClass, and then next comes the name that you're going to give the class. So we'll call it neural network. And then you have to list the fields. Remember, we said the fields are the variables. Those are the variables that are listed here are referred to either as fields, member variables, class member variables. Okay, different names that we could use, but usually, hopefully, we don't use the word variable, but I probably might anyway. So anyway, and this is a list of fields, and it begins with an open parenthesis, so it has to end with a closing parenthesis. So first you give the name, comma, then you give it fields, which is set into a list, then comma, then you give the methods, which is also set into a list, and then comma here. Comma here. So, no, sorry, that's wrong. Wrong. That's not the comma. Sorry. The first method is here. So this is part of the list. And you have to close the method like that. And then comma. And then the next method and comma. This is all within this list. These commas are occurring. So we're listing the different methods or functions that we want. So we're going to want a forward, a backward, a JCost, and we usually we need a special function called initialize. The initialize function will tell R how many elements have to be filled in when you create an instance. Remember, we said we're going to create an instance like this. Like that, right? In this case, we need we have to fill in how many arguments to get the instance. We have to fill in 4. So the initialize method will say that there are 4 fields that will need to be filled in to create a student. So the initialize method here the initialize method here will give the stuff, will say what fields will need to be filled in order to create an instance of our neural network class. So like here I said we only need, like here I said we just need these 3. So that would have been described in the initialize method. Okay, so that's one of the functions, one of the reasons to have this initialize function. Okay, and then after you do that, then you're finished with the methods list. Comes down, the end of the methods list is here, and then the end of the set ref class is here. And then you will have written your class. So you'll put in all the methods that you want, you put in all the fields that you need, and you're done. Okay, then will have written this class. So in this example, so the fields are going to be the input, the X variable, the input. The hidden layer size is also going to be a field. The output, the learning rate, and some other thing here that is just arbitrary, not necessary at all. It's just something I threw in there because I wanted to have it in there for just some silly purpose. So anyway, but you can have as many fields as you want. And here we tell R that the input has to be a matrix. So if it's not a matrix, it will complain. We say that the hidden layer size has to be a number. So if it's not a number, it will complain. This has to be a matrix. This has to be a number. This has to be a character, or a character vector, I guess. So anyway, that's what we have. Now, sometimes we'll be more flexible, and instead of saying matrix, you could just say any, and then you're not putting any restrictions on it, so it won't complain, but it also won't protect you from making mistakes. So it depends what you want. And then we have the methods. We're going to have prop, back prop, forward, JCost, initialize. Okay, so we have, and then once we do it, this is going to be the way that we want to use it. So we want to have the inputs. This is the number of nodes in the hidden layer, the outputs, the learning rate, and this thing that's not important. Okay, so then you have to write the initialize function to say that this is what you want to have as inputs when you create an instance of your neural network class. So you have to say, I want a matrix, I want I guess this is a number. I want a matrix, I want a number, and I want a, okay, I guess this is like a vector, just a vector, sorry. A vector can be just a single number, and this can be just a single something. Okay, so these are all vector style. Okay, so this is where you say it in the initialize method. So you say it in there. So that means now that you're going to have to write this, to create this neural network, you're going to have to fill in 1, 2, 3, 4, 5 things like this. And then you do you say that this thing is going to be assigned to this to this, right? So this thing, the first thing that's filled in here, that's the first thing here. This is going to be assigned to this field, and then you okay. So because there are 5 arguments, the arguments are assigned. Okay, for example, this. Okay. Now it says, note that all the assignment operators, all the assignments use the super assignment operator. So you can see that, well, you can see that here. So this uses this. Have we used this yet? Did we use that yet or not?
I think we did once in the last chapter, but we didn't talk about it.
Okay, we skipped it. So, well, I had the wrong name for this actually in the original text. I called it the global assignment operator, and the global would mean that that if we create such a variable like this, that it would be in the global environment. You know, we know what the global environment is, and it would be in the global environment. That's not true, actually. It just goes up to the next level in the environment hierarchy. So, you know, there's an environment hierarchy, right? You're in a function, so that's an environment. And then you go outside of that function, there's an environment there. And then if that was in another function, then you could go outside of that and get to another environment. And eventually you might get to the global environment, or actually there's a few even above the global. Sounds like, anyway. So anyway, that is the, so this is called not the global assignment operator, it's called the super assignment operator. It just takes you up one level. It doesn't take you all the way out to the global. So anyway, but we're doing that. Note that all the assignments use the super assignment operator. This is generally true for all methods in the class. Many, if not most, variables defined inside methods will be needed outside the method. So if we need this outside of the method, then we have to use the super assignment operator. Recall that assigning them to be non-local variables accomplishes this. Local variables may be created inside the initialize method if their purpose is only to facilitate calculations within the initialize method. But a lot of these, like this one, we need it outside of the definition of the method. So we use this to do that. Okay. Now, we also cover in this chapter something called batch updating, which I'm not going to cover because we don't need it for chapter 14. But it's very interesting, and the math is interesting for it. But the idea is that so far, when we train our neural network, we take one example of the data, we push it through the neural network, and then we do the backprop, which adjusts the weights, all the weights, and then we go back and we get the next instance, and we push it through, and then we do the backprop for that and adjust all the weights, and we do it. That's the way we designed the neural network. So we designed it to handle one variable at a time. One variable gets pushed through, backprop. Second variable gets pushed through, backprop. But there's an alternative way to do it, which is to take the entire data set, push it through as like a matrix. Push it through as a matrix, and then calculate the average of all of the gradients that you would get for each one of them, and then do that backprop based on that. Hang on one second. Okay, so then do the backprop based on pushing the entire matrix of all the data through, doing some sort of averaging, and then backprop. So that's called batch updating. And you don't have to take the whole data set. You could take like the first 100, push them through, backprop. Next 100, push them through, and backprop. So you could do it that way. So that's batch updating. The math in there is interesting, but we're not going to do that because we don't use it in chapter 14. Okay, so that's that's the basic idea of chapter 13. Now, I'm sorry, chapter 12. And let's go to chapter 13. There's just one idea in chapter 13 that we need as well. And that is this, adding in a bias term. So we haven't done this, but we definitely want to do that. So let's look at this picture here. Now, this is more simple than we ever considered, but it's good for illustration. So let's say we have a node here and a node here and a weight there. And as always, and as before, to calculate y, we take x times w to give us y. Okay, so in other words, we're doing this. Y equals wx. So that's what this diagram represents. That's what kind of function this diagram represents. Okay, everyone clear about that? Okay, now, however, this is extreme. Now, suppose we were using this network to try and model some relationship between two variables, between x and y. You know, like we say, like the distance that, that the number of hours you sleep affects your test score. So what's the relationship between the number of hours you sleep and your test score? Now, if this was a picture of the model that you're using to make that, to express that relationship between the number of hours you sleep and your test scores, it's extremely limited. It's a linear function, very, very limited. You know, why should it be linear? Why should the relationship between test scores and hours slept be linear? It's just extremely limited, and so it's not going to be very accurate. And so the error in your predictions is going to be bad. It's going to be high. So this is not very good. Now, actually, in this case, I'm not complaining though. In this chapter, I'm not complaining about that. I'm complaining about the fact that this doesn't have even an expression for the y-intercept. In other words, this function has to go through the origin, right? Right? If we have this, if we have this and this, then that relationship, it can have any slope, but it has to go through the origin. Like maybe the slope could be high, but it still has to go through the origin no matter what. So W will determine the slope, but W will determine the slope, but there's no y-intercept here. So it means that you always, your model, this is your model, has to go through the origin, even though the data doesn't look like that. So that's the thing that we're complaining about in this chapter. So for example, suppose you had this data. So when x is 0, y is 2. When x is 1, y is 3. 2, 4. So this is 0, 1, 2, 3. And this is 2, 3, 4, 5. And if you graph that, you get this. And here is the x-axis. I'm sorry, here's the y-axis here at 0. So this data goes through, has a y-intercept of 2. It has a y-intercept of 2. But our model is not going to be able, is going to do a miserable job of trying to model this data. So, you know, that's very limited. And we're going to be stuck with a high error, a high J, right? We're never going to be able to reduce the J very much. So we'd rather have, this is the actual, this represents the data actually. Y equals x plus 2. Let's just check that. So when, if we take x plus 2, I get that. I take x plus 2 here, I get that. If I take this plus 2, I get that. So this is y equals x plus 2. Okay, which is clear from here. Y equals x plus 2. So we would rather have a model, not just like, not just something times x, but something times x plus a constant. That would be a much better model. Does everyone recognize what I'm talking about? So here I'm just saying instead of W, I'm calling it A1. And then we want to have another constant term here. I mean, another coefficient here, A0. So this would be much more flexible. So how can we represent that as a diagram? So this diagram represents something through the origin, but I want a diagram that isn't stuck being through the origin. So this is how we do it. So we have the same diagram, x and y, and then we're going to add this extra node here. And this is called the bias node. And, you know, obviously, you know, we've been talking about, we have many x nodes, right? We have 2x. Actually, we've talked about having 2 input nodes, but we could have had 3 or 4 or 5 or as many as we wanted. But anyway, so we still have the same thing. We still have a bunch of nodes here, the input nodes, which those input nodes accept the data, right? That's what they're for. They accept the data, right? We put in the data. But this one doesn't take in data. So the way it works is we set it to 1. So it doesn't take in different, you know, when we go and get a new example of our data, and then we feed it in here and here and here and so on. But there's nothing to feed in here because these represent our data. So this is just set to 1. Always, no matter what these are. However, there is a weight here, and there is, of course, a weight here. So how do we calculate y now? What's the calculation of y now? It's x w1, and as typical, this, but this is not x, this is just 1 WB. So we get XW1 plus WB, which is what we wanted. This is what we wanted, right? We wanted to have a constant term or a y-intercept. So by doing that, by throwing in this extra node here, we are allowing for this. And then we are not stuck in the origin anymore. Okay, does everyone get this? Okay, so this is called a bias term. It's always set to 1, but the weight is trainable. So that means that we can, just like this weight is going to be trainable, so that we can figure out the best slope, we can also figure out the best y-intercept. Okay, is that clear? So this is trainable, right? The weights are, this weight is trainable, and that allows us to find the best slope, but this also allows us to find the best y-intercept based on the errors, based on our training algorithm, right? Based on our gradient descent and back prop, right? So both of these are trainable, and so we can hopefully improve them through our neural network magic, right? Okay, so, and then if you have more layers, so here I added in the bias, and the bias is connected to every node here. So there's a weight here, there's a weight here, there's a weight here. And then this layer also will have a bias, and that's connected to every node here. Here, there's only one node, so it only one, but we could have more than one node here. We could have more layers as well. Okay, so that's the way it's done. So there's a weight for each. And this gives us, obviously, some additional flexibility. Okay, and that is all we need. Or now the rest of the chapter is just how to take our existing code and clean it up somehow so that we can add in the bias. So anyway, it's pretty. Anyway, you could read it if you have time, but we're going directly to chapter 14. Okay. Now, chapter 14 and 15 are the powerful examples of the neural networks. Now, the reason they're powerful is that we're using OOP, and we're using it in an intelligent way. In that chapter 12, it was just sort of a play example, but here we're using it in an intelligent way. And what we're going to be able to do with this intelligent way is, well, actually I have it here. At the end of the code, I could show you at the end of the book, at the end of this chapter, okay, at the end of the chapter, we are going to be able to use our code in the following way. We'll create a new instance of our neural network. This is an alternative way of creating a new instance. So you can do it like this, actually. So we're going to create a new instance of our neural network. It's going to be called net. But net is going to have a function, a method called add. And what we're going to be adding is the different layers into the neural network. So just by writing this, we're going to be adding a layer with 2 inputs and 3 outputs. And then we can add what we call the activation layer, which means we can add in the activation layer means we can add in the sigmoid function, but we don't have to use the sigmoid function. There are other choices we can use. Here we're adding in the inverse tangent or the hyperbolic tangent, which looks almost, if you saw it drawn, you probably wouldn't know that. I don't think we'd know that it's different from the sigmoid function. I forget. Maybe there's something about it that we would know. But anyway, so we're going to add, anyway, you can add in the kind of function you want in between this layer and the next layer. And here we're adding in a layer that has has 3 and 1, but we could add in as many layers as we want here. So we could create all kinds of architectures and test them all out. And we also can decide on the error function that we want. So we have an add function. We also have a use function, which allows us to use to change how we measure the error. Like we've been measuring the error in a certain, in a natural way, but I think we mentioned that there are other alternatives. I think we said that we could use the absolute value to measure error instead of the mean squared error, which squares. We had a square in our measure, but we could use the absolute value instead. So we could choose here, we can test out different error methods. Here, MSE is the one we've been using, mean squared error. And then then we're going to write a function called fit, and that is going to take our training data and fit it to a model. In other words, it's going to do all the work. It's going to run all the back propagation and all of that. And so the fit is where all the back propagation happens. Okay, and then we can run it, and we get the answer, and we can see that the error decreases very nicely. And then we can do the same thing with. Then in the next chapter, we want to learn how to build all the new fancy architectures, not just what we have here, but we talk about the architectures that people have come up with recently to do image recognition, for example, and that's called convolutional neural network. And there we create some new kinds of layers, new kinds of layer architectures, and they work much better for image recognition. And we can use the same style, though, to add in all kinds of, any sort of arrangement of these new layers that we want. We could have a certain new layer here, and then a different kind of layer here, and then another, and then this one again, and so on. We could do anything we want. So this style of programming is far more powerful than having to write it all the way we did it before. And this allows us to be much, much more flexible. So we want to learn how to do this. So that's where we're headed. Okay, so today we will start that discussion out. Now, what we're going to do, though, well, first of all, we're going to do this. Now, this is looks like our sort of like our neural network was before, but it's not really the same thing, because if you look at it, look, there's a weight here, and then you multiply that weight times this to get Z2, but this picture is not the same because now we're splitting up that node. Remember, there was Z2 and A2 were in the same node before. Everyone remember that? Right, we had Z2 and A2 in the same node, but here we have Z2 here and A2 here. So this is kind of a different representation of our neural network. So here, what we are doing, the reason we're writing it this way is to say we're going to treat each process separately. So when we go from here to here, that's one process. And when we go from here to here, that's another process. Now that makes sense, right? It was kind of a little bit strange to have both of these in the same node because they are separate processes. So it was a little, I'm sure in the back of your mind, it sort of probably bothered you at least unconsciously, that these were both in the same node. So we're not doing that when we write it like this. So each node represents its own process. Now, one difference, therefore, is that we don't always mean multiply. When we go from here to here, we mean multiply x times w1. But when we go from here to here, we don't mean multiply. We mean apply this function to f2 to get a2. And this is called the threshold function, or the activation function. And it was the sigmoid function. So we would take this and put it in the sigmoid function to get this. And then we would multiply this times w2 to get this, and then we put that in the sigmoid function, and so on, right? Does everyone follow this? Okay, so that is but that's what we want to do here, is we want to think of this as separate processes. That's going to be the key, very key, because you saw we want to be able to add pieces, so we have to think of everything as a separate piece. So that's one thing. And then we saw before that we had Z2 equals X1 plus the bias. We had the bias before. Now, if we have several inputs, what is the equation that we want? We want to have X1 time plus the bias. Oh, sorry. So we want to get, how do I want to say this? How do I say this? Okay, so remember we got Z2. Oh, sorry, here's the picture. Sorry, here's the picture. Remember we got Z21, Z22, Z23, right? So how do we get Z21? We take X1 times this plus X2 times this, right? Everyone remembers that. So that is Z21. Let's just call it Z1. That's Z1, Z2, Z3. So that's Z1. So here, how do we get, this is Z1. So how do we get Z1? We take, wait, we need the bias picture as well. Okay, so we take this. Oh, sorry. Okay, so this diagram doesn't work the way our diagrams worked before. So get rid of your model of how to use this diagram, because it's not the same. But what we mean by this diagram is we take X1, there's a weight here, X1 times this weight plus this bias, right? Now, isn't that right? Let's go back to our bias picture and make sure. So in fact, maybe we better do that. Let's go back to our bias picture. No, where is that? Here. Let's go back to this picture here. So what is Z1? Let's write it down here. Okay, let's write Z1. Can't see that. Clipboard, brushes, tools. Here. Okay, let's write Z1. Z1 equals what? So Z1 equals X1 W. I'm just going to call it W. So I'm just going to call it W1. I don't want to write all this out. X1 W1 plus X2, and I'm just going to call this W2. X2 W2, and then plus what? Plus basically the bias is just 1. So plus, now in this next picture, we're going to call the weight, this is kind of weird, but we're going to call the weight the bias. Okay, so we're not, like before, I said let's call it W sub B. So W sub B, okay, I'll leave it like that. But then we're going to change it, actually, in that picture that I was just showing you. We're going to change it to, we're going to write it like this. Maybe you don't like this, but that's the way we're going to write it, bias. Okay, so the bias means W sub B. So I know bias, we called this node bias, but bias is the weight. We're calling the weight the bias. Okay, so this is what we have now. This is how we calculate, this is Z1. We take this times this weight, plus, we're going to call this the weight on here, the bias, plus the bias. Okay, now let's go back to what we just saw. So here, so let's see what this, how should we read this picture? We want it to be, we want this to be Z1, or this is Z1. We're using Y1, but in this case it means Z1. So we want this to be what? We want it to be X1 W1 plus X2 W2 plus the bias. So how do we read this? X1 times the weight, then this means plus the bias. So it's not, it doesn't look like, even though we drew this with the lines and the circles and all that, we're not interpreting it as this is this times that weight and this times that weight. That's not what that's not the way we're interpreting this drawing. So we're completely reinventing, or this drawing doesn't mean what it meant before at all. Don't read it the way it was before. So this drawing just means, how do we get this? We take this times this plus that. We take this times this plus that, which is exactly what we had. This times this plus this times this plus the plus this. Sorry, we take this times this and this times this plus that gives us that. So this diagram means this, actually. So maybe you don't like this diagram, but anyway, that's what it means. And the other thing is that notice that I called this W, I called this Y, and I called this Y, and I called this Y. But before we were calling it Z1, or we might have been calling it Z, or actually we were calling it Z2, or we might have been calling it Z3, and so on. But that's the other change that we want to make in our thinking is, and it doesn't seem like it's very important, but it is important. We're going to call, whenever we have an output, we're going to call it Y. Instead of calling it Z and Z1 and Z2 and so on, we're just going to refer to it as Y. So we're not going to be sort of taking account of what layer it comes from. And when we go from here to here, remember we said we're going to call that a separate process. When we go from here to here, we said we're going to call that a separate process. And we're going to call the output of going from here to here also Y. So this is going to be called Y. And this is going to be called the input into that process. So we're going to take the input of the process, apply the sigmoid function to it, and get the output of that process, which we'll call Y. So we're always going to be talking about inputs and outputs in terms of X and Y. Now, that doesn't seem like it's a big deal, but it helps us a lot in terms of making this modular transition. So transitioning to a modular approach. Okay, so the input is not going to be called, going from here to here, it's not going to be called Z1, it's going to be called X. And the output here is not going to be called, or Z2, it's going to be called A2 or whatever. And then going from here to here, the input is not going to be called A1 or A21, it's going to be called X. And the output is not going to be called Z31, it's going to be called Y. And the same thing here. So we're going to treat We're going to treat everything as inputs and outputs. All right, is this clear so far? Okay, now let's go to here. So how did we're still using Z here. So how did we get, I just showed you how we got this value, right? We said we took this times this plus this times this plus this gives us this. So in other words, what I'm saying is to get Z2, let's just confirm it once more. To get Z21, what do? We take this times this plus this times this plus the bias. Does everyone get that? Or we wrote it here also, right? We take to get this, we get x1 w1 plus x2 w2 plus the bias. Now, let's look at this. So this says to get z2 sub 1, z2 sub 1, or z2 sub j, what do? We take, let's look at this, we take x times its weight, next x times its weight, next x times its weight, as many as we need, and then we sum all those up, and then we add in the bias to get this z. Did everyone follow this equation? So, this is an example of this equation. Now, just let's make sure that these indices are right. Are these indices correct? So to get the jth item, in other words, in this picture, you know, this one is the first one, this is the second one, this is the third one. To get the jth one, what do? We take we need all of the x's, so we take this x, x1, and we multiply it times what? W1j, because we go here. And then we take this one, this will be W2j. So what is it? It's, you take the x, wi matches the x, and j matches this. So that is right. So this is the correct indices to do the calculation. And then the bj is, that picture doesn't have it. But anyway, if we had something down here, it would be W, well, anyway, we're calling it, the one that connects to here is called BJ. The one that connects to here, so we have this node down here, but it's going to be a weight here. So we're going to call that B1. We're going to have a weight, the node here connects to here, where they're going to call that B2 and B3. So that is BJ. So this tells us how to get the output, this output. This tells us how to get this output. And this is the same as this, as long as we know how to read this. You know, this is a new diagram. It doesn't read the way the other our other diagrams read. But anyway, so this is the expression that we've been using, as long as we include the extra bias term here. Okay, does everyone follow this? Okay, so we have this now. Okay, now, so this kind of, so we said we're going to look at it like this, and here, this kind of process is going to be called a fully connected layer. In other words, this kind of process here is called fully connected. Every node here is connected to every node here. And same thing here, every node here is connected to every node here. That's called fully connected. But when we go to the next chapter, chapter 15, when we're doing image recognition, we use nodes that are not, we use layers that are not fully connected. So we do something different. We might have, like 100 nodes here, and so, maybe another 100 nodes here or whatever, but we don't have fully connected. For some reason, we do it, we want to have other kinds of layers. So, but in this chapter, all our layers are fully connected, or these layers are fully connected. But this process is not actually fully connected, because when I go from here to here, I don't go from here to here, and this doesn't affect this A2, and this doesn't affect this A2. So actually, I'm only going from here to here. So this won't be fully connected. When we go from here, when we go from this level to this level, that's not fully connected. Actually, I forgot, I misspoke. Even in this chapter, sometimes we're not using fully connected, because when we go from here, this layer, remember we're treating this as a separate layer, that's not fully connected, because this only affects this, and this only affects this. There's no relationship between this and this. So this is actually not fully connected. And this is the activation process, right? We say we apply the activation function here, 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 here. So that's called the activation layer. And it's not fully connected. I made a mistake. So, so we have fully connected layers, and they're linear. They're linear. This is basically linear. Linear means there's no squares on the x's. There's no cubes. There's that kind of thing. It's linear. This doesn't mean square, of course, right? We said this just tells us the layer. Has nothing to do with squaring. So this is linear. So this is a linear layer. So it's fully connected and linear. So we call it linear, fully connected. So we talk about it, and we describe how to write the output of it. I mean, the output is just, the output is this, right? We have a Z1, Z2, Z3, but now we're calling it Y1, Y2, Y3, and so on. But we have the output of it. And so we saw that this is the equation for the output, for the jth output. And we want to write this in matrix form for the whole output, the whole input. So we can do that here with this setup, which we'll talk about. But we write the whole Y output basically as this matrix X times the weight matrix W plus the bias matrix B. So this will work, but we'll go into it in more detail. But this will give us what we want. Okay, so that's going to be an expression for that. And then we want to talk about, here's the new part. We want to talk about the back propagation just for this layer. So that doesn't seem to make much sense. How can we talk about back propagation just for a single layer? Back propagation involves this, right? What does this mean? Tell me, somebody, what does this mean? Somebody tell me what this means.
It's a partial derivative of the cost respect to the weight.
Right. So isn't that exactly what we need for back propagation?
Yes.
Yeah, that's exactly what we need. But somehow we want to write our code so that, how do I say it? Somehow we want to write our code so that, how do I say this? So that our code so our code is going to have a code is going to be a function, right? We're going to have functions, of course, right? We have functions. So we want to write our function, our back propagation function, so that what it does is it calculates, it changes the weights for a particular layer. So we want to have a function which takes some inputs, whatever inputs we decide we want it to take. So we want to have a function which takes some inputs, whatever inputs we decide are important, and then somehow it does all its work and changes the weights in that layer. That's the way we want to write this code. Let me say it again. We want to say for a particular layer, we want to have a function that takes some inputs. We're going to write the function so we can decide what the inputs it's going to take are. And it's going to take those inputs and it's going to do some stuff. But by doing that stuff, it's going to change the weights in that layer. Okay? That's what we want to write. We want to write a function like that. And we want to write it in a way so that we want to write this function in a way so that it doesn't matter which layer we're talking about, it's still going to take the same kind of arguments and use them to change the weights in that layer. Okay, so that is what we're trying to do. We're trying to write sort of a generic backpropagation function, which will take some arguments, and we can decide what the arguments we're going to construct it to need, because we're going to write the function. It's going to take the arguments, do whatever it needs to do, and depending on the type of layer it is, it's going to change the weights, because different layers need to work in different ways. Because remember, what do we mean by a layer now? Or did I say that? I think I said it. What do we mean by a layer now? This is one layer. This is another layer. This is another layer. This is another layer. That's the way we're thinking. So, so different layers are going to have to do different things. Like if this is the layer, you know, what is the backpropagation? How does it have to change the weights? Well, actually, there are no weights here. But anyway, there could be weights here. I mean, if it was a different kind of layer. So anyway, but we want to write this backprop function so that depending on which layer it thinks it's at, that sounds strange, but depending on what layer it thinks it's at, it will perform backprop in the appropriate way. Was that clear or not clear? Is that clear or not clear?
Can you try explaining it again?
Well, it's pretty hard to explain it without showing it. But what I'm trying to say is we're going to try and write a backprop function that, depending on the layer it's in, it's going to take some stuff, right? Functions always take arguments. So it's going to take some arguments, going to do whatever it has to do so it can change the weights for that particular layer. So that's called modular. So it's going to depend on the layer, but it's going to do it one layer at a time. So what we're going to actually do is we're going to start at the most downstream layer, right? When we do backpropagation, we start close to the J, so the most downstream layer, and then go layer by layer back. So we're going to actually have a loop that does backpropagation for the most downstream layer, then the second to most downstream layer, then for the next layer, and so on and so on. So we're going to have a loop that loops through all the layers and does this back prop at each layer. So changing the weights. So that's kind of modular. And so if we write it that way, then it doesn't matter really how many layers we include. It's just going to go boom, 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 boom. It's going to loop through all the layers and do it each time. So that's how it's going to allow us to easily be able to add many different layers. So because we're going to write it so that it just goes through a loop, does the back propagation for the first layer, the second layer back. When I say first, it's kind of like the last, right? But whatever you want to call it. The one closest to the end, then the one before that, then the one before that, then the one before that, and so on. So that's how we want to write our code. Now, I said it's going to loop through. It's going to loop through the layers. So actually, we're going to put the layers into a list. We're just going to have a list of the layer names. And it's going to go through. So we can loop through that list. So we'll say, do it for layer one, do it for the last layer, do it for the layer before that, do it for the layer before that, do it for the layer from that. We're just going to have a loop. And then, so as many, and that add function, remember I said add down at the bottom, there was add. Here's add this layer, add this layer. That add function, all it does is it adds this layer to the list. So we're going to keep adding layers to our list, and then we're going to loop through that list through all the layers. So that's part of the structure of the code. So this add function, all it does is it just adds the name of the layer to the list, and then we're going to loop through that list. And so, so that's kind of giving you a hint about what the structure of this program is going to look like. Okay? All right, now let's keep going. So that's kind of what we're trying to do. So, but of course we're going to need this, right? Of course we're going to need that, the partial of j with respect to w. For whatever layer we're in, we're going to need this. Now, the way that we're doing this now, we added in this bias term. So we're also going to need to adjust the biased weights, or the bias. We're also going to need to adjust that. Remember, we said the bias is also trainable, or the bias weight is also trainable. So we need to adjust it, and we need to adjust it the same way we needed to adjust this the w, that is by considering the derivative with respect to j. So we're going to need this as well. And also we're going to need these, because these, remember, we're going to rephrase everything in terms of x and y, right? X is going to be the input and y is going to be the output. So we're going to reterm everything like that. And so we're going to end up having terms like this, because this just means the output. And so probably, the chain rule is going to have this in it, because remember that, the chain rule is a very long expression. Sometimes we had seven terms in it, seven factors in it. And, well, we'll see this in a minute, but we're going to rephrase everything as x and y, and we're going to see that these are actually going to be within the chain rule. These terms will actually be within the chain rule. Okay, so we're going to do that, and we're going to figure out, anyway, in this section, we're going to figure these things out. So we want to figure these things out for this linear fully connected layer, because we're going to have to do back propagation for this for all our linear fully connected layers. And then, so we sort of figure it out in general, and we'll go through that. And then, we also go figure out this thing for the bias term, how we have to figure this out so that we can adjust the bias weights. And we need this and this, we'll see that. And then we can code it. We can code the fully connected layer after we figure that stuff out using the results that we figured out here. So we figure out what this is, we figure out what this is, and this I said this is, well, this we need to explain a little more, but we also figure this out. Then we can, we need to code these because we need to know what is partial j with respect to w, right? Because that's what we're going to use to update our weights. And maybe it's just as simple as this, which is pretty simple. So that would be nice. And then we could just code it. This is very simple to code, right? It's just a transpose of the input, blah, 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 whatever. It's simple. And so we do the math here. We figure out what these things are that we need, and then we have to code them, whatever they are. And then after we code them, then we go to the activation layer. That's a different type of layer. And we need to figure out still some derivatives. This is a picture of the activation layer because we take an input and we put it into our activation function and we get the output. So this could be a sigmoid function, or it might be a different function. But this is the way we go from here to here. And this is not, as I said before, I made a mistake. This is not fully connected, right? We don't have a connection to here and here. It's just here to here. This is not fully connected. So activation is not a fully connected architecture, or it's not fully connected. Okay. Anyway, then we need to figure out the whatever the derivatives are in this case, and we figure out back propagation for the activation layer. And we do a little math there, and we end up with a very simple situation. So anyway, whatever we get, then we code that. We code the activation layer. And then we have the last part is we have to make our neural network class. We already figured out how to do all these layers, but we haven't made the class yet. So we need to write the class. So that means we need to have this add function in there. That's what we want. We want to be able to add layers. So we're going to write a neural network class that has an add method in it. And then we'll just add the different layers like we saw. And then we also need a fit method. And that's going to, once we add in all the layers, then we're going to run all the back propagations. We're going to run back propagation for the first layer, then the second layer, then the third layer, then the fourth layer. Then we're going to throw another piece of data, another example through the network. We're going to push it through, and then we're going to run back propagation through the first layer, then the second layer, then the third layer, then the fourth layer. And then we're going to keep doing that. So that's what the fit method will do. It's going to run, it's going to push one piece of data through the entire network, then run back propagation, back propagation, back propagation, back propagation. Then it's going to take the next and push it through to the end, then run back propagation, back propagation, back propagation. So that's going to be a loop. Going to go like that, then again and again. So that's going to be the fit method. So we have to write that. And then we said we're going to have this as simple, but this is just to choose. We included here an option so that the user can choose the error function they want. So we've been using something called the mean squared error. That was our J function, but it looks like this. Looks like, right? Our J function looked like this, right? We had that, and y minus y hat, right? And then actually we had a 1/2 there, which we may not need, but we have that there. but we could have, maybe we would have, maybe we want to look, we want this, y minus y hat absolute value. Maybe we don't want to use square, we just want to use absolute value. That's okay. So you could write a function like this pretty easily and then use that as your activation, as your error function. So you could write your own error functions and then use them by putting them in here. That's what this is going to allow us to do. Okay, so we do all of that. We define our neural network class here, and we have the list of the methods here. We have the add method. We have the use method. We have the predict method. We didn't talk about that, but that's just to make predictions. We have the fit method. Fit method is the big one, the most important one. And that's where the backprop happens. So hopefully somewhere in this fit method, we'll find the backpropagation, a reference to the backpropagation function. So if we scroll through here, first of all, the fit method also needs forward propagation because it has to push the data through and then go back. And then hopefully we also see that it also contains backpropagation. Okay, so it does. And it's doing it layer by layer. You can see that how are we calling this backpropagation method? It says layer dot backpropagation. So that's kind of weird. What does that mean? So that means we'll have different layers, and each layer will have its own backpropagation method, because the equations were different depending on the layer, right? If it's a fully connected layer, of course, the way you do backpropagation is completely different than if it's a activation. In fact, the activation, there are no weights, right? So there's nothing actually to change. So anyway, but depending on the layer type, we'll do a certain type of backpropagation. And this is the layer. You can see that we're looping through layers. So layers, like I said, is the list of all the layers that we have. So we could add in, 100 layers if we want. So that then layers here would be that list. And so layer in layers. And this reverse means start from the end of the list and go backwards. So we're going to go through all the layers from this side all the way back, and each one we're going to run its backpropagation method. So that's what this does. So that's the beauty of this style of programming, that this will say if it's one type of layer, it'll run one type of backpropagation. If it's another type of layer, it'll run a different kind of backpropagation. So that's the beauty of this method of object-oriented programming. So anyway, we're going to go through all the layers. And so we're going to take one example of the data, which happens here. We're going to take for J in all of our data, from the first piece of data to the last piece of data. So that's a loop. We're going to take that first piece of data, and we are going to push it through all of the layers, forward propagation through all the layers. We're going to forward propagation for layer in layer. So this is a complete loop through the entire set of layers. So for each layer in the layers, we're going to push it through. That's what this does. Now, once we've pushed it through, then we want to do backpropagation, and we're going to do that for each layer in the layers. We're going to run backpropagation. We're going to pick up the results, and okay, well, we'll have to go into that in more detail. Okay, so that's what we have to do. Now, without going to the rest of the detail yet, because I just want to explain what we're going to, no, actually, let's keep going. Well, no. So anyway, we're going to test it, though, on a certain famous problem. So this problem came up in the 1960s when neural networks were just being invented in the 50s by this guy. And then these guys said, your theory is a bunch of crap. They said, this neural network stuff is nothing. It's bull. It doesn't work for anything. It's useless. These guys at MIT, they said that. And their argument was that there's this function. Now, we studied logic. We studied the AND connector. We studied the OR connector. We studied the if-then connector. And we studied the not P connector. So we studied all those four. But remember, when we studied the OR connector, we talked about the example where if you have a child and you say to your child, you can have chocolate cake or you can have ice cream. And then if your child has both, what do you say? Suppose they have ice cream and cake. Do you punish them or not? You can have ice cream or cake, and then they have both. What do you do? Anybody? You bring out the whip or not? Anybody here?
Yes, Professor.
Did I lose everybody? I hope I didn't lose everybody. This is a very important subject, what we've been talking about today. Are you still here?
Yes, still here, Professor.
Okay, do you punish or not punish?
I think you will.
You will. And how about somebody else? Anybody else here?
Not punish.
What? Not punish?
Yeah.
Okay. All right. Anyway, in English, it's not clear what that word or means. But here, we want to make it clear. So we have the exclusive or means if you were using the exclusive or, then you would punish them because you mean you can only do one or the other, not both. So the truth table for the exclusive or is if they do both, that's false. It's not true. They didn't follow the rule. Okay, so anyway, it turns out that the exclusive or is nonlinear. Now, a nonlinear function. Now, you might think, well, what do you mean by a function? The XOR is not a function, but it is a function. The inputs are here, and the output is here. And if you don't like these inputs, you can change them to zeros and ones. So you have these inputs, give you these outputs. That's a function. So, but it turns out to be a nonlinear function, and the original neural networks couldn't model even this very, very simple function. So that was their that's how they dissed this guy Rosenblatt. They said your stupid neural network can't even model this thing. So that actually research stopped in neural networks for about 25 years because of that. But eventually, they developed the backpropagation using, that we've discussed, that has the gradient descent. And so that made it, really improve things. And so now if we try our neural network on this, we get excellent results. In fact, I was just testing it here. And well, let's watch it. Let's watch it here. Let's run it. Let's see what happens. Okay. So if I look at the results, I ran it 500 times, and the error is like tiny, 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 right? You can see it. The error started out higher. There, higher. Here, yeah, the error started out much higher, but as we trained it, it gets much better. So if they had done this, if he had done this at that time, they wouldn't have stopped working on neural networks. But anyway, so that is what we are confronted with, and it works well on this problem. Now in chapter 15, we apply a different structure. We use a different architecture. We make some new types of layers, and we apply it to this data. And we are able to get the machine to recognize, that all of these are 3s, and all of these are 4s, and all of these are 5s. So the computer can recognize this. Of course, we can see it, and we can, but the computer, it only has, this is an image. So there's a picture here that is in this area here, and there's just a bunch of pixels. So some of them are white and some of them are black, and that's all the computer sees. It doesn't see anything. It doesn't see anything. It just gets this vector of pixel 1 is white, pixel 2 is white, pixel 3 is white, pixel 4 is black, pixel 5 is whatever. It just gets that long list of pixels, and somehow it's supposed to know from that the list for this and the list of this are the same, represent the same thing. And we can get it to do that by constructing certain kinds of layers, which were developed from 1995 to 2006. When they solved this problem was 2006. So anyway, we build that network. We need different layers than we've talked about before. Okay, so we don't have any more time now, but we want to come back and go through the math and more details about this modular approach next week. Well, just very quickly, this was the kind of thing we confronted before, right? This was the partial of J with respect to the weight in the first node. I'm sorry, in the first layer, right? And we had to go through this long chain rule. So this is dj, and then all the way down to dw1. Now, I think that we said, well, this part here, we called it delta something, delta 3 or delta 2 or delta 1, whatever it was, delta something. So anyway, this part here, we can call this whole part here that I tried to highlight dj dz3, right? We can summarize it as dj dz3. And then we're left with this part here. Now, if we look at this, we can see that all of this part, dj dz3, happens before we reach the first layer of weights. right? This is Z3. So, if we go back and look at the picture here, Z3 is here. So this is stopping right here. So all of this stuff that happens is not in there. So so this is what's left over here. And this takes us from Z3, A2, A2, Z2, Z2, W1. Okay, well, we're stuck there. But the idea here is that we want to get this. Remember, we want to think of a layer as having an input and an output. That's the way we want to visualize this for programming purposes. So that's what we have to discuss next time. Okay.